will use Gauss unless you're in the superconducting magnet. This is one thing I want you to emphasize to the students. The second thing I want you to emphasize to the students was this. You know, the magnet. We said the magnetism is the moving charge and moving charge interaction. But magnet, where's the moving charge? The moving charge, the molecular current inside the magnet. So still it's the current and the current interaction, okay? These two things I want you to emphasize. Now you can start now, okay? When are you there?
Hey, Dr. Chin, yeah, sorry, I was muted. I'm here.
Okay, did you hear what I said?
Yeah, absolutely.
Okay, good. Go ahead. Go ahead.
Okay. Hello, everyone. I think we have most people, most students today. Okay, so we'll start. Last time, I think we left off in this slide when we were talking about Biot-Savart law. So let's take a look at Biot-Savart law once again. Before we had derived, or we have more accurately described the relationship between force in a moving charge, right? The magnetic force, a moving charge in a uniform magnetic field at a constant speed, and we found out that the force is, of course, proportional, directly proportional to the magnitude of the charge and the cross product of the velocity in the magnetic field. So all of that is over here. F equals QB cross B. And then we said that it can also be the same, okay, for a current carrying wire. So if you have a wire like my charger, like my phone charger, some current will flow in one direction, and that current will create a magnetic field around it, right? And then this length vector is the same as the direction of the current, okay? But the magnitude of that will be the distance of the wire. Yes, I will share the slides with you. I think I just sent you an email a few minutes ago, I think half an hour ago. So you may check that email. I don't know if some of you were able to watch the video on Lenz's law before we started, but if you didn't, I'll just show you a very brief part of the video that's more relevant to what we're going to talk about today, which is partially, you know, we're going to finish this chapter, and then we're going to move on to Faraday's law of electromagnetic induction. So, but today, we're going to continue on to Biot-Savart law. So we already know that the force is directly proportional to the magnitude of the charge and the cross product of the velocity in the magnetic field, okay? Assuming that this magnetic field is uniform. And so now these guys from France, Biot and Savart, came out with a formula, with a relationship between the magnetic field and a moving charge, right? Because essentially what magnetism is a relationship between moving charges, right? Just like Dr. Chin emphasized. And it's also similarly as in electric fields, right? Electricity is nothing but an interaction between charges, regardless of their motion. Okay, so they could be moving or they could be standing still, but there will still be an electric field coming out of the charge if it's positive per se, radially outwards, or radially inwards if it's negative. Okay, so but then you might think, well, if the charge is moving, this electric field will not be constant, right? Because it's moving, and so this electric field will be moving as well. The electric field lines will be moving as well. So all of this will have some relationship. Magnetism and electricity will be related no matter what. But nobody thought about that until Oersted. And well, Oersted, I think we are going to talk about Oersted a little bit later. So I'm going to leave that for later. Now, let's talk about Biot and Savart. So here we have the relationship, okay, between the magnetic field and a moving charge, right? So imagine that this over here is the moving charge, the red positive charged particle. Okay, so this over here is the moving charge, right? And it's moving in that direction of the speed, right? V, which is this green vector. So it's moving in this direction. So imagine that. And then what's going on is that the charge will create, okay, a magnetic field at point P. So this is point P over here, okay? And the distance between the positively charged particle and point P is going to be R, right? It's going to be called R. But we're going to also define a unit vector along the direction towards point P, which is nothing but R hat. Okay, so this is going to be R hat over here. And so this, disregard the R hat in this direction and this direction, is nothing but the direction at the same points in magnitude, because there can also be considered point P's. Okay, but we're looking at this one specifically. So over here, we have that the magnetic field is proportional, of course, to the force, right? So it's going to be QV cross R hat. This time is not going to be crossed with the magnetic field, but with the unit vector pointing along this line towards point P, R hat. And remember that a unit vector, the magnitude of a unit vector is 1. So in essence, what you're going to get is that the magnetic field, so if you find the magnitude of the magnetic field due to Biot-Savart of a moving charge, you're going to get that this is nothing but mu0, which is the permeability of free space. So this is a new constant that you have seen now. Permeability of free space, mu0, divided by 4 pi. Okay, divided by 4 pi, and then multiplied by the magnitude of the charge q and the cross product of the velocity, okay, the magnitude of the velocity and r hat, which is nothing but a sine of the angle between them. So if the angle between them is phi, you're going to have v, the magnitude of v multiplied sine of phi. Okay, so that is only if there is an angle between the velocity vector and r hat, the unit vector, pointing towards point P. Now, if we were to consider these points over here, the story will be a little bit different, because the angle between r hat and v will be 90 degrees. Therefore, the sinus will be a maximum. So sinus of phi will be 1, and you're going to have mu0 over 4 pi times qv times sine of phi, which is going to be 1, divided by the square of the distance between the charge and the point P. So this is our law of a moving charge. But now, let's think about how this is going to be related to a current wire, because we already derived an expression for the force due to the magnetic field of a current wire. So over here, you know that it's going to be, the force is going to be proportional to the magnitude of the charge multiplied by the cross product of the length vector L with the magnetic field, which is uniform. So we know that QV is essentially equivalent to IL, or I delta L, change in the distance. Therefore, we move into, okay, Biot-Savart law in terms of the current wire, current I. But also, we haven't really talked about this. The thumb rule, the thumb rule is essentially your thumb is going to be in the direction, okay, of this of the current. So let's go to the next slide, and then I will show you what I mean by that. So over here, if you think about this over here, this wire that you see, golden color wire, you're going to have an infinitesimal section of wire, and you're going to call it ds, and that is a length itself, and it's a vector defined distance, okay, and it's pointing along the direction of the blue, okay, vector, which is going to be r hat. In this case, will be along the P point P. So this is the vector r hat. This is the vector ds, which is nothing but the distance vector, and that distance vector tells you in which direction the current is flowing. Okay, so therefore, what I mean by that is that the current is, what's coming with my mouse? current is flowing from here, okay, in that direction. It's going that, right? Because the blue vector ds is pointing in that direction. But now we're considering, right? We're assuming that this current carrying wire is not uniform, right? It's just in any shape per se, right? Because but you know, you don't have to worry too much about non-uniform irregular current carrying wires, because most of this uh, will be covered on circular loops, okay, or semicircles. We're also going to think about infinitely long wires, so you do not have to worry about the general cases, right? So we're going to think about the specific cases when we have circular loops of wire or semicircular loops of wire. We're going to see how the magnetic field behaves. So we're going to see what happens when you have different combinations of semicircular loops with different directions of current, and we're going to see what happens to the magnetic field, okay, when it's uniform. So if you use your thumb rule, the thumb is the direction of the current, so put it right there. And if you look at the wire, right, and you know that the current is flowing from the bottom up, then you're going to see that the magnetic field will flow in the direction of the curl of your four fingers. So essentially, it's perpendicular, okay, perpendicular to the current, right? But it's in a radial distance, so it's basically around, okay, in a circular manner. Okay, but of course, the magnetic field the vector field itself is essentially almost infinite, right? It goes from the smallest, even from the closest distance to that charge, to the infinitesimal charge, which is part of that current, okay? The blue, you're going to see infinite, right? But of course, since the magnitude of the magnetic field is inversely proportional to the square of the distance.
Hi, Professor.
Hello. Please mute yourself if you just came to class. So if you think about it, the magnitude of the magnetic field will decrease as a square of the distance, as an inverse square of the distance. So as r goes to infinity, you're going to have magnitude of the magnetic field equal to 0. So this is what happens. So essentially, what you use your thumb rule is just to see where the direction of the magnetic field is. You don't really need that to find the magnitude, right? You just need to see the direction of the magnetic field using the thumb rule. Okay, so this is Biot-Savart law for a current wire. So we have that dB. dB is an infinitesimal contribution of the magnetic field, because the magnetic field over here will flow radially, right? Radially perpendicular to dx. So it will be something like that. Okay. Make a better sketch. It will be something like that, right? Yeah, but it will be in all directions. So it will be in all radial distances, but it will be decreasing as an inverse square of the distance. Okay. So essentially, at this point over here, we will be at point P, according to what the distance between that infinitesimal section of the wire is. But of course, since this is a cross product, even this infinitesimal section over here will also contribute to that. This over here will contribute to that. And so we have something that's an integral. So we integrate, like in all contributions of the magnetic field, okay, from whatever the length of the wire is, right? So depending on how long the wire is. So in this case, we're just looking at a generalization of Biot-Savart law. And so we have that the infinitesimal contribution to the magnetic field is nothing but mu0 over 4 pi times the magnitude of the current times the cross product of dx and r hat, the unit vector pointing towards point P, divided by the square of the distance. Mu0, the vacuum permeability of free space, is 4 pi times 10 to the power negative 7 Tesla meters per area, per given area. So over here, I'm going to show you, I think I don't know if we showed you last time. I think we were talking about how the speed of light can be determined based on the permeability of free space and the permittivity of free space. So the speed of light c is nothing but 1 over the square root of mu0 multiplied by epsilon 0. Okay, so if you put that in your calculators, um, you're going to get something close to 3. Okay, this is just an approximation. This is not exact. This is 3 times 10 to the power meters per second. And the speed of light, which tells clearly that electricity and magnetism are very closely related. And when this comes together, we're going to talk about later, is what's called electromagnetism. Okay, electromagnetic phenomenon, which is essentially light, right? An electromagnetic wave will be nothing but light. Okay, so then we integrate on both sides.
Yeah, the story is this, because people have already measured the speed of light long ago. It's about 3 times 10 to the 8th, meter per second. Then when Maxwell came, then he derived the equation. Then he found out in the equation is the wave equation. The wave equation, the wave propagation speed is, as Juan said, the square root of epsilon 0 mu 0, right? Then Juan said if you can calculate epsilon 0 mu 0, the square root inverse, then equal to 3 times 10 to the 8th. So then Maxwell said this is not accident. Measured light speed, people measured. It's 3 times 10 to the 8th. The electromagnetic, you derive it, it's also a 3 times 10 to the 8th. So the Maxwell said this is not accident. So that's how he predicted light is a form of electromagnetic wave. So this, I think, when said a very profound, fact. I used to put this question in the graduate students to the qualifying examination. Some people cannot answer it. Now you know it. Okay, that's very good. Fine, continue.
Now you know one of the most fundamental ideas of the universe, the speed of light, and how it's derived. So the wave equation, of course, but you're going to have to take physics 3 if you want to go more in depth into that, right, to find out how to write it more closely. But now we're just going to talk about the overall stuff, overall phenomenon here with Biot-Savart. So here I have an example for you to think about. Okay, now we just talked about how the thumb rule works, and also using Biot-Savart law, right? But here you don't really need Biot-Savart law. This is just a thumb rule problem. So over here, you have to figure out which of these wires, okay, A, B, C, D, or E, will have the right direction of the magnetic field at point P. Okay, so for example, at point P for wire A, we're going to have, okay, a current flowing downwards, right, in the negative Y direction. And so we know that the magnetic field has to be radially, okay, coming out of that wire. So radially from here, it will be decreasing in magnitude as an inverse square of the distance. So at point P, we would like to know what direction of the magnetic field. We don't really need the magnet. So use the thumb rule, okay? So just think about it and let me know what you get and drop down your answers on the So anybody would like to answer the question? Okay, so somebody asks, what's the difference between C and E? Well, here, what's going on with C and E is that, okay, let's say for this wire, for wire C, the current is flowing out, right? For E is the same thing. Now the problem is that point P is on the right for wire E and point P is to the left of wire E. So which one has the correct direction of the magnetic field? Using the thumb rule. So go ahead. All you have to do is use the thumb, and in this curling the fingers around it will show you in which direction will be the magnetic field. So I'll tell you what happens for A, right? So let's look at A again. So if you see the current is flowing down, right? So you use your thumb rule, thumb has to point downwards because that's the direction of the current. And so the magnetic field has to go radially around that thumb, right? So, but now you're thinking in 3 dimensions, and you want to make sure that your 4 fingers will be, okay, they will be tangential, okay, at point P. So you have to think about what's going to happen, okay, and then you just curl your fingers. And so if you imagine what's going on, okay, at point P, what's going to happen is that the direction, okay, will be out of the pitch. So it's coming out of the pitch, right? Because it's coming tangential, okay, to that circle. So let me try to somehow. So let's say that this over here is the direction of the magnetic field, right, in a radial direction. And so over here, clearly this has to be coming in the perpendicular, in the tangential direction. But now you have to think in 3 dimensions, so it's coming out of the page. Somebody asks, how do we know how to use the right hand or left? Now, let me emphasize this. For finding the magnetic field due to a moving charge, okay, you have to consider the sign of the charge. So if it has a positive sign, you use the right hand, right? But that's only for a moving charge. But now, when we're talking about current, current is a flow of electrons, so you only use your right hand for that. Always use the right hand, the right hand, okay, for to find the direction of the magnetic field for a current carrying wire. So that's the only thing. To find the force, okay, due to a current carrying wire, you also use the right hand. But then if it's for a moving charge, it's different. You have to consider the sign of the charge. So if it's an electron, you use your left hand rule, okay, or you could use the right hand and then remember that it's negative sign, so you switch the direction in opposite direction that you get. Now in this case, what you do is you use your right hand, thumb, and fingers to curl your fingers around the thumb and find what's the direction of the magnetic field. So at A, what's happening is it's coming out of the pitch, but it says that it's going into the pitch. It's not right, right? So think about it. For B, it can be possible, right? Because it says that the magnetic field is going up. So it's not, somebody said C. So for C, if you think about it, current is going up, right? The magnetic field is going in radial direction. It's going in a circle, right? So at that point, okay, in the plane of the page, okay, this is the page. In the plane of the page, the direction of the magnetic field will be into the page, tangential to that circle, into the page. And so the answer choice, the right answer here will be C. Yeah, you got it. Very good. Okay. All right. So now let's talk about the specific cases of Biot-Savart law. We already know how to integrate very basic integrals over here. So I think it's fair enough to take a look at this. So for this example, we're going to take a look at a circular arc. Okay, so this is just a given arc with some angle phi. Okay, so we have an angle phi over here, and we have a radius r. Okay, so supposing that it will be a full circle, we will have a radius of r, big R, capital R, and so this is the direction of the current. Okay, flowing counterclockwise on that arc, and so what's going to happen is that if you use your thumb rule, right? So if you use your thumb rule for that arc, you're going to find out the direction of the magnetic field at point C, right? So at the center of this of this arc will be outwards, right? So it will be outside, coming out of the page, okay, radially in that direction, in the radial direction. So it's coming out of the page at point C, and all of it is coming out, okay, at point C. So if you were to have a circle, a complete circle of wire, you're going to have a total magnitude of the magnetic field at the center of the page, okay, coming out of the page. But it's also anywhere inside of this circle. You have the magnetic field coming out of the page, but of course it will be different in magnitude this time because you have to consider all the contributions, okay, for all the infinitesimal parts of that wire. But now for this specific case, you're going to have an arc with angle phi, okay? And so we know that if IDS is perpendicular to R, we know immediately that the cross product of ds and r hat, right? Because this over here is going to be ds, right? So this blue vector is ds, but then r, which is the distance between point C and the one infinitesimal part of the wire, has a unit vector coming out of the infinitesimal part of the wire going towards the center. This is r hat over here. And so when you take the cross product of a unit vector perpendicular to another vector, you get that the magnitude of the unit vector is 1. So we get rid of r hat, and we only left with the magnitude of the s over here. So now we're over here. E is equal to mu 0, the permeability of free space, divided by 4 pi, multiplied by IDS, divided by r squared. Because we know that the distance, the radial distance will be r, right? That's the radius. And that's nothing but, okay, using some basic calculus, we say that we are going to take an infinitesimal part of that angle phi. So then we're going to call that infinitesimal part of the angle d phi prime. Okay, so let's call it d phi prime. So we have an infinitesimal contribution, right, of the angle. Then this over here has to be d, right? And it's flowing in that direction. Okay, and then r hat will be like that. And so we have that mu 0 IDS divided by 4 pi times r squared is nothing but mu 0 ID phi prime divided by 4 pi times r. And we brought up, okay, the angle in here multiplied by the radius, because we know that the arc length ds, the infinitesimal arc length ds, is nothing but the radius of that arc, okay, the radius of what would be that circle r, multiplied by the infinitesimal contribution of the angle d phi prime. So what happens is that if you were careful to observe, 1r is dropped in the denominator. So basically, this cancels out with 1r over here, and you get 1 over r, right? And then what we can do finally is integrate in terms of d phi prime. So we integrate both sides from 0 to phi, right? Because the total angle is phi. And we're only looking at an infinitesimal contribution of the angle d phi prime. So we integrate from 0 to phi. And that this is nothing but mu 0 I, the current, divided by 4 pi times the distance r, and all of that multiplied by phi, which is the total angle. And this is, of course, in radians. And so from this, we can find out what's the magnitude of the magnetic field for any angle phi, right? So this is a general case for all circular loops, okay, or arcs that belong to that circle. Somebody asks, why is it phi prime? Why is it phi prime? Well, I told you that the whole angle, right, is phi, right? But now because we want to find out what's going to be the contribution of the magnetic field for the whole angle, we have to think about in infinitesimal terms, right? So we have to think about an infinitesimal angle d phi prime, right? The d means it stands for differential, which is infinitesimal. Physically, right, it means it's very small. And so, no, don't worry. And so you get that that's equal to mu 0 I over 4 pi r times the angle phi. And so let's say that you want to find the whole contribution. So now we're going to think about a whole circle, right? So if you have a whole circle, and what's the angle of a whole circle in terms of radians? It's 2 pi radians. So if it's 2 pi radians, substitute 2 pi by phi, and then you cancel out 2 pi on the bottom and 2 pi on top, and you're left with this over here, with b is equal to mu 0 times the current divided by 2 times the radius. And this is the case for all loops of circular wire, okay? And then you can find the magnitude of the magnetic field at the center. Now, let's say the current is flowing in the opposite direction, then of course the direction of the magnetic field at the center will be in the opposite direction as well, because it has to be perpendicular to it, right? So you use the thumb rule to find out where the direction of the magnetic field will be at the center, and then you find out it's going to be into the page if it were to be clockwise. If it's counterclockwise, it comes out of the page using the right-hand rule. Okay. So now, here's exercise for you. It would be what would be the formula for the magnitude of the magnetic field for a 45-degree angle, 180-degree angle, or 4 pi radians? So think about that momentarily. Okay, so basically, all you have to do, right? You know that to convert angles in degrees to radians, you multiply by pi over 180. But if you already memorize your unit circle, it's easy for you. So then you might say that, for example, this over here, if it's 45 degrees, that's nothing but pi over 4 radians. And this 180 degrees is pi radians. And 4 pi radians, right? It's already in radians, so you don't have to do any work. And so you just substitute those angles into the formula we derived, okay, using integral calculus over here. And so we say that for 45 degrees, substitute 5 by pi over 4, then we get that B for 45 degrees is nothing but mu 0 I multiplied by the angle, which is pi over 4 in radians, right? Divided by 4 pi times the radius. Pi is equal, and we get that 1 over 4 times 1 over 4 is 16. So we that is nothing but 0 I divided by 16 times the radius, okay? And you can do the same thing for all angles. It doesn't matter which angle it is. As long as it's in radians, it will work perfectly. All right, some examples over here. You have so you have to find B, for example. They ask you to find the magnetic field B at point B for a short straight wire. So now you use Biot-Savart law now because you know you want to know what's the cross product between r hat and ds. But because ds and r hat are in the same direction, right? You know that it's going to be 0 because the cross product between two vectors in the same direction or in opposite directions, meaning anti-parallel. So parallel or anti-parallel. If these vectors are parallel or anti-parallel, the cross product will be 0 because the angle between them will be 0 degrees and 180 degrees respectively. And therefore, when you take the sine of that, the sinus of that angle, you get 0. Okay, so that's why we don't consider the contributions of straight wires. So if you think about what's going on, and over here, the magnitude of the magnetic field of the center is 0 because r hat points towards the center, and so does the current. Now for this, it's opposite. But we know that the sinus is 0, and so we only consider the semicircular part. We know that this over here is the angle in radians is pi, right? 180 degrees. We substitute the angle, okay, into phi, and then we get that it's 0 I over 4r, okay? Using the generalized formula we found with Biot-Savart law over here, right? This formula. So let's say that you want to find the magnetic field due to half loops, okay? But now these half loops have different directions. And so for this one, for the first half loop, you have two loops that flow in the same direction, right? Clockwise. So if it's in the same direction, it's nothing but the same as if it were a full loop, right? So it's going to be mu 0 I over 2r. So it's the same as a closed loop. If they are parallel, right? So if one is going clockwise and the other one is going counterclockwise, well, intuitively, you're going to know that the magnetic field will be 0, provided that the current is the same for both wires, right? And you have the two semicircular loops, okay? All right, an iClicker question for you. Unfortunately, there are no iClickers, so don't worry about that, but you can drop the answers in the chat. 3 loops below have the same current, okay? The smaller radius is half of the large one, and so you're going to rank the loops by the magnitude of the magnetic field at the center of each combination. So you're going to rank them from greatest to least. So which one will be the answer? Okay, anybody else? Okay, very good. So it's going to be answer choice B. So first you look at 3. It's going to have the least radius, which means that since the magnetic field is inversely proportional to the radius, then if you have a very small number in the denominator, that becomes a huge fraction. So you have the greatest magnetic field for 3, and then for 1 you have the second greatest magnetic field because half of it is half of the radius of the big one, right? So look at this over here is half of that, right? So this is r and this is r over 2. Okay, the same goes for this. And then the magnitude of the magnetic field will be less than 3 because you have a larger radius for the other half, right? You have a larger radius. And then for the second one, you have all the radial distance. Okay, so you have a full closed loop. They'll have the least magnetic field, right? Using you can take a look at it. You can do it mathematically to prove it for yourselves. But it's intuitive to just take a look at what's happening in terms of relationship between the radial distance, right, and the angles. The answer choice will be B. All right, so now let's take a look at the magnitude of the magnetic field, okay, nearby a long, thin, straight wire that's carrying a current, all right? And so we're going to use the same result that we had, okay, but now this one was derived in a different way. So this was mu 0 I divided by 2 pi times A, okay? So A would be the distance, okay, between that point that you want to find the magnitude of the magnetic field from and the wire itself. So it's perpendicular to the point P. Okay, so then we use Ampere's law, right? Because remember that Ampere's law is nothing but the closed loop integral of the magnetic field dotted with dl, right? So cross loop the closed surface integral of b dot dl is equal to permittivity of space times the enclosed current. Okay, so this is Ampere's law. What you do is that if you want to find the magnetic field due to a long wire, so what you do is that this over here into the page. So the direction of the current is going into the page. Okay, so you can imagine the wire going like that. Right, so this is my charger. So it's going into the page like that. Current is flowing into the page, and so the magnetic field will flow in the radial distance of the wire, like that. And so what's going to happen is that if you use Ampere's law, you're going to draw an imaginary Amperian loop. So suppose that this is point P. This is point P over here. And let's say that the distance between the wire and point P is A, right? So that's what's going to happen. So essentially, we draw an imaginary Amperian loop. It's a circle, right? Loop is a circle. It has a radius of A. And so to use Ampere's law, you take the magnetic field out of the integral because it's a uniform magnetic field. And this current is not changing. And if the current is not changing, the magnetic field will be uniform. It will be a constant, right? In terms of magnitude, that direction is different. Okay, so it's not constant in terms of a vector. Okay? So what you do is you take magnetic field out of the integral, just take the closed loop integral of dl. The closed loop integral of dl is nothing but the perimeter, okay, the circumference of that loop. Circumference is 2 pi times the radius is a, so you get that the magnetic field is going to be mu 0 pi enclosed divided by 2 pi times the radius a, and that's how we get that. So using Ampere's law, okay, one of Maxwell's equations. Okay, so then we find that the relationship between the radial distance and the magnetic field is 1 over the inverse of the first power of the radius, right? So it's different from Biot-Savart law. Okay. So now You can use the right-hand rule to find the direction of the magnitude, of the magnetic field. And clearly it's shown. So if you use the thumb as the direction of the current into the page, the magnetic field will flow like that, clockwise, right? So in our perspective, it's going to be clockwise. Okay, so this is the same, much the same example in different positions, right? So the wire, let's say that the current is flowing to the left over here. So it's going like that. So you use the same thing. You use the same method, the right hand, the thumb rule. So it's going to flow like that. And now you want to make sure you're using the plane, right? The XY plane. And so for the top part of the wire, the direction of the magnetic field will be into the page, right? Because my fingers are pointing into the page. And then if I curl my fingers down, then the top of the lower part of the wire will experience a magnetic field that's coming out of the page, right? So that's what the dots represent. So this is the same case for all combinations. You use the thumb rule. Thumb rule is your best friend for the exam is the thumb rule and the right hand rule. All right, now let's think about what happens when you have two different wires, right? Suppose it's two currents, and then you're going to have distance between the wires. Let's call that distance D, the separation D, right? And so we want to find out what's the force that is acted on by each wire, right? So we know that by Newton's third law of motion, for every action there is an equal and opposite reaction. For instance, if we think about the force that wire B acts, okay, on wire A, will be the same thing as the force of wire A on wire B, right? By Newton's third law, we know that equal and opposite forces. For every action, there's an equal and opposite reaction. So then, using the previous equation that the previous formula that we derived, B equals mu 0 I over 2 pi A, we can find the magnitude of the force using this relationship, okay, of the force, which is proportional to the cross product of the length vector in the magnetic field times the magnitude of the current. So what you can find is plug in your magnetic into the force equation, and then you can find the force, okay, due to two current wires. Okay, so some important takeaways from this is that if the force is attractive, right, it's going to happen when these currents are parallel. So if the currents are in the same direction in both wires, then you're going to have an attractive force, right? The wires will come together, but then if they're in the opposite direction, they will repel. Okay, so that's a takeaway from that for the exam. So now, like I said, you just plug in the magnitude of the magnetic field into the force equation. You get that the force per unit length. So you basically all you do is divide by the length L, right? So it's the same thing as if you multiply, right, by L on both sides. So if you were to multiply by L on both sides, you get the force as its own, right? But now usually in the exam they will ask you questions like, oh, what's the force per unit length, right? That's the keyword, per unit length. When they ask you for the force per unit length due to a current wire on another current wire, then you have to remember that you're thinking about two wires, right? Two wires with currents flowing in whatever direction they tell you they're flowing, and then you use this concept. You use the force is equal to mu 0 times the product of the two currents in both wires, divided by 2 pi times the distance, multiplied by the length, right? But then if you are going to find the force per unit length, you divide by that length L. So that's why we have F of A on B divided by L. Like I said, from Newton's third law of motion, F of A on B is equal to the minus of F of B on A. Okay, so we have a attractive force, right, per unit length of the currents in this case because they are parallel to each other. You can use, the right-hand rule for each current. So usually, what you want to do is you want to take one wire at a time, right, to find the force. So you want to take a look at in this case, In this example, we're taking a look at current flowing in this direction, bottom. So you're taking a look at this wire. This is going to be your central, uh, basis for solving this type of problem. Defining the formula, let's say that you forget the formula, but it's unlikely that you are going to have issues with that because it's going to be on the formula sheet on the day of the exam. So you use your thumb rule regularly, right, to find the direction of the magnetic field. And of course, over here, what's going to happen is that so you're looking at the wire on the bottom, right, in this example. But then you want to find what's the force that's going to be applied on by A. So for that, you use the right hand thumb rule for the top wire to find out what's the direction of the magnetic field on the bottom. So you see over here that this crosses, the yellow crosses represent the magnetic field going into the page. And so if it's going into the page, right, you can use the right hand rule. So for the bottom wire, right? So it's like one of those problems that we were doing earlier. So the current is flowing in the direction of my index finger. The direction of the magnitude of the magnetic field will be into the page, and so the force will go up, right? Just like the green vector arrow will show you. Okay, so here is an end view. Okay, so it's just you're looking at it from the top, right? So you're just basically turning the wires and looking at what's going on. Okay, so you can clearly see what's going on. Wire IB is going to be attracted to wire IA. But the same thing happens for wire IA. It's going to be attracted to IB by Newton's third law. Okay, so here you have an example. Two wires, okay, are 1 centimeter apart. Okay, so the distance D is 1 centimeter. And each of the currents is the same, so it's 100 amps. So what you're gonna do is find the force per unit length. What's the force per unit length? Okay, so go ahead, plug that into your calculators if you have one, and let me know what you get, and see if we are consistent with the slides. I'll give you a couple of minutes to do that. Remember that the permeability of free space, okay, is 4 pi times 10 to the negative 7. Okay, Teslas times meters per unit area. So this is mu zero. I think that if you have the calculator TI-36X Pro, you can find a section in the calculator that will give you a set of constants, right? And this is pretty useful, actually. You can find Faraday's constant. You can find a lot of different constants, and I think mu zero is definitely in that calculator. So this is the calculator I'm talking about. So if you're on the exam and you are not going to have enough time to type, right, 4 pi times 10 to the negative 7, what you do is you go to your calculator, TI-36X Pro, right? You type second, and then you press on constants. There's a button over here that says constants. If you press on there and you scroll down, you're going to find different constants. You have the speed of light, you have Avogadro's number, and you have both the permeability and permittivity of free space. So remember, for electricity, you have permittivity, right? And then for magnetism, you have permeability. So it's two different words. And it's denoted by epsilon 0 and mu 0. So you just click on that, and then you just click on the constants. So it's much easier, right? And faster. So it's a shortcut. Somebody said 0.2 centimeters, 0.02 meters, because oh, you said 0.02 meters. Because we're looking for the force. What's the force in Newton per unit length? So newtons per meter. That's what we're looking at. Somebody said 2 newtons. Okay, so let's take a look. Somebody got 0.02, but they got the 0.2. Yeah, so look. So you have the you put in mu 0, right? Mu 0, which is 4 pi times 10 to the negative 7. That cancels out with 2 pi on the bottom. So that's why you're left with 2 on top, right? Multiply by that twice, the square of the current, right? Because the current is the same, and divided by 0.01 meters, and you get 0.2 newtons per meter. Okay. So you got 2 newtons probably because you forgot to change your units from centimeters to meters. So don't forget the relationship, right? 1 meter is equal to 100 centimeters. Okay.
Huh?
My slides are a little bit frozen for some reason. Okay. Skipped ahead a little bit. All right, so now here's another example for you. We have different sets of wires, right? So over here we have A, B, C, D, the answer choices. And then you're going to be looking at the wire on the center. Okay, so you want to know where the force, okay, the net force will be 0 on the center wire. So you're focusing on the center wire over here for each answer choice. So find out what's going to be the magnitude of the force for each section, and then let me know what it is. Well, unfortunately, they show the answer already over here. But then justify. Okay, can somebody justify why it's A? Somebody asks, what is the unit for mu naught? Mu 0. So to find the unit for mu naught, okay, using, let's say you can use this equation. Solve for mu naught, right? You already know what the units for V are, it's Teslas. You already know what the units for R are, so it's going to be meters. And for I, it's going to be amps. So if you solve for mu naught or mu 0, okay, that's going to be magnetic field multiplied by 2 pi R, okay, divided by the current. So if you think about this in terms of units, for V you have Teslas, so the units for mu 0 will be nothing but Teslas multiplied by 2 pi R, okay, which is nothing but a distance, and it's in meters, so Teslas times meter divided by amps. Okay, so these are the units for mu naught or mu 0, the permeability of free space. Okay, so for this problem, okay, somebody justified the. So he says, Aaron says, fields that are equidistant from the center and pointing in the same direction, but on opposite sides will cancel. Yeah, so it's pretty trivial to find, the force, okay, to find where the force is 0, because all you do is you use, you use the fact that when you have 2 wires with the anti-parallel direction in currents, they're going to have a 0 force, right? And so over here, what's going to happen is that this and this, okay, will cancel out. So the forces due to these two will cancel out because they're anti-parallel, right? So the net force will be 0 acting on this over here, and then from the left, the same thing happens, right? So what happens is this wire will cancel out with this, okay? Because they're in an anti-parallel direction. So that's what's happening for this problem. All right. All right. So now let's talk about Ampere's law. I think I already used it for one of the problems, right? To derive, we derive the magnetic field due to a long straight wire. So over here, B is equal to mu 0 I divided by 2 pi A using Ampere's law, right? So, but I didn't really talk about it. Well, I just said it was one of Maxwell's equations. And so Ampere's law is going to be, like I said, the closed loop integral of B dot DL or B dot DS, DS, DL, the same thing, which is nothing but mu zero times the enclosed charge, current. Okay. Ampere's law can also be derived from Biot-Savart law. Okay, so that means that tells you that Biot-Savart law is pretty fundamental. Okay, for this, but in essence, what is more fundamental, okay, will be everything, right? Everything is based on Coulomb's law. Coulomb's law is the more fundamental law in electricity. Okay, so a lot of times textbooks will emphasize Ampere's Gauss's law to be the more important law over here, the more fundamental one. But in reality, what we have is that you know Coulomb's law is the more fundamental one because this was determined using the same process that was used to find the universal gravitational constant by Isaac Newton. Isaac Newton came up with this equation, which is equal to the product, okay, of two masses, right, divided by the square of the distance between them, and multiplied by universal gravitational constant. This one is extremely similar to Coulomb's law, so it's extremely fundamental. This law, the universal law of gravitation, was derived by Newton in the 1600s. It was a long time ago, and I think Coulomb came up with this later. And it was like a long time ago. So can you think about like how hard it could be to actually come up with these things in times where technology was so limited? And of course, K was found out was determined by Cavendish using the Cavendish balance, right? To find the forces due to two charges, two particles that have charges in them. So that is the most fundamental law over here. But Maxwell's equations gives us a more general idea and a more practical view of what electricity and magnetism is. And so Ampere's law can be derived from Biot-Savart law, and Biot-Savart law pretty much comes from Coulomb's law. But I'm not going to go much into the details because really this is not what NJIT will test you on. Okay, NJIT will test you on your ability to use these equations to solve physics problems in electromagnetism. Okay, so over here we have an Amperian loop right on the bottom, and what this is trying to tell you is that, well, an Amperian loop doesn't necessarily have to be a uniform circular loop, right? It doesn't have to be a circle, okay, for it to be usable. So it's an imaginary loop, right? This is what is the most important part of Ampere's law and Gauss's law is that you use imaginary surfaces and loops to find magnetic field magnitudes or to find the current. Okay, let's say that you know the magnetic field, so you just take the integral of beta ds, right? So sometimes the magnetic fields could be non-uniform. It could be changing, right? So it could be as a function of time, distance, etc. But for this course, 100% of the time, the magnetic field will be constant. So you don't have to worry about that. All right. So usually for Amperian loops, what you're going to think about is the direction of currents inside of the loop. So let's say that over here in this Amperian loop that has been drawn, right? We're going to consider the counterclockwise direction to be positive, right? So counterclockwise direction is positive. And so the current that goes in that loops, right? So the cross-sectional area of the loop will experience a flow of current. And so whatever current flows through that loop will be called the enclosed current, right? But let's say that the current I1, so this current is flowing into the page, right? This is a wire, so this is coming into the page. This is coming out of the page, right? In that case, if the currents per se have the same magnitude, right? So they have the same magnitude in amps, then that means that if they're in the opposite direction, the enclosed current is zero, right? So the total current coming into or out of that loop is zero. So then that means that the magnetic field will be zero. Now, usually you will never consider currents outside of an Amperian loop if you were to find the magnetic field on any point along the Amperian loop. Okay, so any point along that Amperian loop, find the magnetic field as long as you know what's the enclosed current inside of that loop. All right, so here's an example. To find the magnitude of the magnetic field outside of a long straight wire. So you use Ampere's law. We already derived this in one of the problems over here. So we said that it's going to be 2 pi r. Okay, so the circumference is 2 pi r. So therefore, V is equal to mu 0 divided by 2 pi r. And then from that, we can find the magnetic field due to a long thin wire, right? Using Ampere's law. Okay, so here is how it goes. The magnetic field will always be tangential, right? We talked about how it's using the thumb rule that you find the direction of the magnetic field. So if it's tangential, okay, you're looking at how the direction of the magnetic field is with respect to ds, which is the infinitesimal length vector. Okay, so this is the infinitesimal contribution of that wire, of that magnetic field around the imaginary loop. So an infinitesimal section of that imaginary loop, which is ds, is in the same direction as B, right, the magnetic field. And because this is B dot ds, right, the dot product, remember the dot product, B dot ds is nothing but the magnitude of B times the magnitude of ds. Okay, so, and that, okay, will give you the same thing as, multiplied by cosine of the angle between them. So if the angle between them is theta, okay, you say cosine of theta. And so over here, you know that the angle between them is 0. Cosine of 0 is a maximum. It's equal to 1. So you just get B times ds. Okay? And so that is why it's pretty, easy to integrate because it's always in the same direction, right? ds is always in the same direction as B. Okay, so now we're going to talk about what happens if, per se, we're going to find the magnitude of the magnetic field when we draw an Amperian loop that's inside of the cable. This over here is going to be the cable with a distance of r, right? With a radius of r. So this is just the cross-sectional area of that cable with radius r. And suppose that we want to draw an Amperian loop inside of that cable. Now, if that's the case, we know that the magnetic field will not be constant, right? If the radial distance decreases or increases. So we're going to see how that changes, okay? So if we draw the Amperian loop, which is in yellow, right, in golden color, inside of that cross-sectional area of the cable, which is coming out of the page, right? So the direction of the current is coming out of the page. Over here, we have a dot, so that means it's coming out of the page. Then what you have is that you're going to use cylindrical symmetry, and you want to find what's the density, right, of current. You want to find how much current is flowing, okay, with respect to the total current. And so what you do is that you find the ratio of the areas, the cross-sectional areas from the Amperian loop. So the area of this Amperian loop will be pi times the radius of the Amperian loop, little r squared. Okay? And the area of the entire coaxial cable, so the entire cross-sectional area of the cable will be nothing but pi times capital R squared. Take the ratio of the currents flowing through both areas to find the density. Okay, so the ratio will be that the enclosed current, okay, is equal to the total current, right, multiplied by pi r squared, which is the area, okay, that is inside of that imaginary Amperian loop, divided by the total area, pi times the capital R squared. So using this fact, right, you can plug this enclosed current into Ampere's law. So over here, we know that beta ds, the integral of beta ds is b times 2 pi r, because we know that it's going to be a line integral along a circle. So the distance of that circle would be 2 pi r. Okay, and so what you have is that you plug in your enclosed current, right? I pi r squared divided by pi capital R squared. The pi's cancel out, so you have, it's going to be 0 times I times little r squared divided by big R squared. And in this case, it's important to remember that little r is not constant, right? So little r is our variable. Here, what's changing is the Amperian loop's radius. Okay, so the total radius, which is capital R, is not changing because, you know, that'll be physically difficult, you know, to expand a cable of wire. You know, I don't know how you do that. You have to have a mechanical tool to do that. And besides, you have to increase, right, the current flow into that. Or, well, you don't really have to, but you have to add more wire. You have to add more copper wire to increase the area, right? But that's not the case here. So what's changing is the Amperian loop's radius. That's what's changing. That's what's going to be the variable. So here we have a nice graph describing the relationship between the magnetic field, okay, the magnitude of the magnetic field with respect to the radial distance r of the Amperian loop. Okay, so essentially what we're looking at is we're looking at the, so let me erase this. So I'll show you what I mean. What we're looking at now is we're looking at what happens when the Amperian loop is over here and then over here. Okay, and all this is from 0, okay, meaning over here, to R, okay, to capital R. So we're going to see what happens when the Amperian loop pretty much outlines the cross-sectional area of that cable. And then at that point, we're going to have a turning point. And what's going to happen is that now, since the current enclosed will always be the same after this, right? It's not dependent on the ratio of the current density. Then what's going to happen is that the magnitude of the magnetic field will increase in a linear manner, right? So it's going to be linear until it reaches the radial distance capital R, and then it's going to fall off as 1 over R, right? Because we know that this over here, okay, is going to be mu 0 I times R squared divided by R squared. So when big R, okay, is equal to big capital R, then you get mu 0 I. That cancels out. And you get the same thing for all distances outside of that cable. So it's going to be 1 over R, because using Ampere's law, right, take the closed loop integral of beta ds, and this R over here is what changes the whole thing. Okay, so that's important to think about. All right, here's an example for you. The answer is literally right there. Hopefully you didn't see it. So what you have to do is using, you know, what you know about Ampere's law now, you have 4 different currents, 4 different wires carrying the same magnitude of current, right? And then you're going to have different Amperian loops, okay, outlined in dashes, right? So you're going to rank, okay, the magnitude of the magnetic field to be negative or positive. To rank it from greatest, okay, from the most positive to the most negative. Okay. So drop down your answers on the chat. I'll give you a couple of minutes, and we'll take a 10-minute break at 7:20. Okay. So drop down your answers on the chat. Hey, Dr. Chen, how are you?
You know, the Ampere's law here we call it, right? The integral I dot dl equal to, integral B dot dl equal to, mu naught or the current inside. Did you prove it? I was kicked out. The phone, you know, that part I didn't hear you.
Yeah, absolutely.
You prove it? Did you do the integral? Prove it?
Yeah, I did the integral. I showed them how beta ds is going to be the magnitude, right, of b times ds times cosine of theta. Yeah. But now because theta is 0, then you're going to have the same.
Okay, now, because this I, has to be infinitely long. Integral should be from minus infinity to positive infinity, and then in the middle, I. But this, I think we have to explain to the students. You don't have to really prove it, but you explain this to it. The other thing is this. In the electricity, we showed to the students, the point charge at the center, and the charge among the charge distributed on a sphere. The electric field outside the same. This is Cauchy's law, right?
Yeah.
Because it's symmetric. Did the book? I forgot. Did the book say the current? Because you have the current. I heard you said the current is distributed. Distributed current is the same as the current at the center. It's a. How do you prove it's the same magnetic field around it? The book didn't say it, right?
No. Well.
Okay, so we don't have to do it.
No.
Let us say if a current is 1 ampere, 1 ampere goes in a very thin wire at the center, then the magnetic field surrounding it as a number. But it's just 1 ampere is distributed in a wire with certain diameter, then the magnetic field is still the same, and that is symmetric.
Yeah,
right?
because
okay, that's good. That's good.
We're looking at Amperian loops that are circular, and the wires were essentially circular cross-sectional areas. Then it would be very easy to calculate.
Yeah. Okay, you have a break. That's good. That's good.
Yeah, we'll take a break at 7:20. So let me get out some answers from.
Okay.
So what do you guys think? What will be the most positive Amperian path? Right. So all the Amperian paths are in the same direction, counterclockwise direction. But then the direction of the current is different. Okay, so you have to find out which one is the most positive and rank them from positive to negative.
Yeah. Okay, good. You have a break.
Okay, so think about that and drop your answers on the chat. Now, one of my hints will be careful with the twists, right, of the Amperian loop. Because when the Amperian loop is twisted, right, like this, then that means that the direction of the current will be opposite, right? So if you're thinking about this whole current, this whole path, you're going to think about what's going to happen if you twist that path back again. So what happens is that the current will go downwards. So it will just go in the opposite direction. So you just have to find, what's going to be the net current. Okay. So you just have to find mu zero times the enclosed current in Amperes. So does anybody want to volunteer to explain the answer? So somebody said D. Okay. Who else wants to suggest any answer choices that would make sense? Somebody said D. So okay, we'll take a look at it. Is anybody else, against that, or do you agree? Do you all agree with D? Okay, so let's look at D. So D says that wire the answer choice 4, right? So over here the path 4 is going to be the greatest. So we have to think about that. So what's happening? We're going to choose the downward direction to be negative. Right? So And that is because the magnetic field, okay, will be going in a counterclockwise direction, right? So essentially, what we're thinking about is that if the current is going up and the magnetic field is in the counterclockwise direction, right? In this horizontal plane, you have to think about it horizontal plane, right? Because the currents are going up and down, and then you have the Amperian loops going in the horizontal plane. Okay? So you have to think about what is the positive and what is the negative direction, right? So we have established that if the magnetic field is going in a counterclockwise direction, then the current that goes up will create a positive magnetic field, right? We will create a positive value for the integral of beta dl. And so we have for let's say for one, right? For one, we have three currents. They're all the same magnitude, right? Going up. So we got three I, and then we got one I going down, right? So this one is going down, minus I. So the total enclosed current will be 2I enclosed. Okay, that means that the magnitude of integral of beta ds will be this multiplied by the permittivity, mu0. Okay, so let's take a look at what's going on in 2, the Amperian path 2. What's going on here is that it's twisted at one of the points, right? So if it's twisted, okay, that means that this current, which seems to be going up, will go down. Okay, so then we just calculate the enclosed current. Two of them are going down, right, and two of them are going up. So 2 minus 2 is 0. So that means that the integral of beta dl is 0. So 0 enclosed charge, 0 I enclosed. Okay. So that means that 1 is probably the greatest, okay, but we're still not sure. Let's take a look at 3. We got a twist over here. So if these two are going up, then we imagine that we're going to twist the wire, right? So that means that the currents will now go down. Okay, so if it goes down, it's negative. And we got as a whole, we got 2 going down. Well, actually, this are going down, and 1 going up. So we got minus 3I plus I, which is nothing but minus 2. And then for 4, if we imagine that we twist this part section of the wire, right? Because we want to make sure that in the end we have a counterclockwise direction in the horizontal plane, right? Looking at it from the up, looking at it from the top. Then what's going to happen is that this 3 that go up will now go down. Okay, so we have every single one going down. So we have minus 4. This one, which looks a little bit more complicated, is basically you just twist each of them. Okay, so if you twist this one will go down. Okay, if you twist this one, then it will have to go up, right? So this one will stay the same direction. Okay, if you twist it now, but if you twist this one, it will go down. So this cancels out with this. This cancels out with this, and this cancels out with this, right? Oh no, this one is going down, right? So you have 3 going down, 1 going up. Okay, so minus 3I equals to. So then we can say that the answer choice, the greatest one, positive one, will be this one, 1. So we have between A and A, right? We can cancel out B, C, and D. And over here we have that the second greatest is 2. So that's true, right? Because it's 0. Everything else is negative. And now second greatest will be either 3. Okay, 3, we found that 3 is minus 2, or 5. Okay, so 3 or 5. So we can put 3, and then we can put 5. So it has to be E. Okay? E is the right answer. And here we will take a break. Okay, so we'll come back in 10 minutes at 7:30. let's get back to this lecture on sources of magnetic fields. Okay, so if you have any questions, feel free to stop at any time and unmute yourself or just type your question in the chat. All right, so let's take another look at another example of Ampere's law. So here we have a coaxial cable for a CATV. Ampere's law has other applications as well. Oh, somebody asks, how can the current be traveling up? You're talking about this problem, right? Do you mean the current on 5? So take a look at it again. Okay, so you have to imagine that you're going to twist the wire. Oh, how can the current be for all of this? Well, not really. For this one, if you twist the wire, then what's going to happen is the direction of the current will switch. It will be in the opposite direction. So
Yeah.
Yeah.
You hear me?
Yeah, I can hear you.
I mean, like if the wire is horizontal, how can it be going up?
Oh no. What I meant was that that all wires are going up or down, right? So it's in the y-axis. But then
Oh, okay.
right, but then the loop, the imaginary Amperian loop, will be in the xz axis. Yeah.
Okay.
So it'll be like horizontal, right? The loop will be like this, horizontal, but then the wires will up and down.
Okay. Thank you.
Okay, so now we can take a look at this. So it's basically using Ampere's law to find the magnitude of the magnetic field due to a current wire. So in this case, it's the same thing, right? So now what's going on is that there's current, okay, flowing here and current flowing here. Okay, so we're going to use 2 Amperian loops, right? So then for this Amperian loop that goes inside of the cable, you're going to have v times 2 pi r, right? Integral of b dot ds will be mu 0 I enclosed, so v is mu 0 I over 2 pi r. But now, if you draw an Amperian loop, right, the blue one, the blue Amperian loop will enclose both the charges in the shield, okay, in this blue turquoise shield over here, and then it will also enclose the current over here. Now, these two are the same in magnitude, okay, and because of radial symmetry, the magnitude of the magnetic field will be 0 because there will be 0 enclosed current. Okay, and that is why for TV cables you have no magnetic field coming out of it. And so if you bring a magnet or if you bring a compass near a coaxial cable, you will see no effect from the wire because outside of the wire you're going to have 0 magnetic field. Okay, so here we're going to talk about solenoids. Okay, so a solenoid is essentially many loops of conducting wire, right? So it could be copper wire, iron wire. It could be any sort of conducting ferromagnetic. Well, it doesn't have to be ferromagnetic. It just has to be conducting, a conducting wire. Okay, many loops of conducting wires. And so what happens here is that if you use the thumb rule, you're going to see that the magnetic field, okay, will go in a radial distance, right, in a radial manner, right, using the thumb rule around each loop. So now, if you have different loops, right, all at the same time, what will happen is that all of these tangential parts, right? So let's take a look at this closely. So what's happening is all the tangential parts over here, right? So this, oh no, that's too thick. Let me get better. So this tangent over here of the magnetic field will be going in that direction, right? So this is B due to this wire. And then you have another tangent over here, okay? And you have another one over here. So what will happen is that the magnetic field inside of a solenoid will be uniform. Okay? So it's like one of those problems when you have a moving charge, for example, right? With a speed v moving in a uniform field going into the page, right? So that's what's going to happen. We're going to have a uniform magnetic field going inside of the solenoid. And then outside of the solenoid, well, we have changing magnetic field. The magnitude will be different for each separation. Okay, so the separation over here is greater than over here, and then over here is greater. So when the separation is greater, you have less intensity and therefore less magnitude of the magnetic field. So then, using Ampere's law, we can derive an expression for the magnetic field due to a solenoid. Okay, so now in this case, we're going to take advantage of symmetry, right? And the fact that b dot ds will be 0 when cosine is 9. So
Now,
that's why we have a rectangular Amperian loop. So
uh,
we have a rectangular,
when you have to tell them, outside the solenoid, the magnetic field negligible, because the Ampere's law is a loop integral. Right? Because you have all these wires go there, so it's mu naught n i's. You have n turns, and all this wire goes in. It's all current. But the loop integral, you have to integral inside the solenoid and outside the solenoid. Outside solenoid is negligible. So that's why you have to you just that's how you calculate solenoid man. So that's why the loop integral equal to b inside the b times the L, the length of the solenoid outside, because the loop is inside a line, then you turn, then goes outside, then it turn. But the turn and outside is negligible. So that's why the loop integral equal to b times L. Negligible. Tell them it's negligible. Okay. Go ahead.
Thank you, Dr. Chin. So yeah, essentially, like Dr. Chin said, the magnetic field will be 0. Okay, will be negligible outside of the coil. But then you can define the number of loops, right? The number of coils you have in the solenoid to be the unit length. Okay, so you're gonna have n divided by L, right? So that's the number of coils per unit length, and we're gonna call this number little n. So capital N, right, is the number of coils, and L will be the distance, the length of that coil, which is L. Okay, so then just call that N, and therefore, if we substitute that into the equation, integral of b dot ds equals to mu 0 times I enclosed, then you have that's nothing but mu 0 times I and h. Okay, and then over here it's nothing but I times n, mu 0 I times n, where n is the number of coils per unit length, okay, inside of an ideal solenoid. And that's because using this rectangular loop, right, the contributions of the magnetic field in the perpendicular sides of that Amperian loop will be 0, right, because b dot ds over here will be 0 since the angle between them is 90, and the same goes with this side. But then for this side, it has some magnitude, right? Because as you see, the magnitude of the direction of the magnetic field is in the same direction as the S, right? Because this will be the direction of that Amperian loop in the counterclockwise direction. So since it's in the same direction, b dot ds is at a maximum, and that's why you bring b outside of that, or okay, is the length, right? It's going to be the length of the total okay, Amperian loop that's being covered, and that is why you only have one H, because outside of the the magnetic field is negligible. It's very mild. That's why we say it's pretty much 0. Okay. So then we can also take a look at the magnetic field using Ampere's law for a toroid. Okay, so a toroid is basically a collection of coils, right, in a circular manner, right? So you have a circular collection of coils. And so when this happens, the magnitude of the magnetic field will be negligible outside, okay, of this collection. So it's essentially like a uniform coil, a uniform solenoid. So now the problem is that the magnetic field will be changing, right? It will be changing in direction, so it's always tangential over here. Okay, so suppose we draw an Amperian loop. In this case, it's in red, right? And the direction of the Amperian loop will be clockwise. Okay, so we have that B dot ds will be equal to B times 2 pi r, right? Because it's going to be a circle. Okay, so we're taking a look at what's happening, what flows current over here. So the current is basically coming into the page. So you're taking a look at each of these wires. Each of these wires has some current. And if you take the total current, enclosed current, you just call it I enclosed. Okay, so that is all the current enclosed by that section of wires that comes into the page. Okay, so of course, if you do the Firm rule, you can see that at each point, okay, at each wire over here. So suppose over here, the direction of the magnetic field will always be tangential. Okay, over here in the inside of the coil of the toroid. So it will be tangential and it will be going in this direction. Okay, just like the green arrows show it. And it's the same for all points. That's why you get a circular magnetic field. So then using Ampere's law, you can say that this is equal to mu 0 I times n, okay, where n is the number of coils, right? N is the number of coils you have in the toroid. So then B is equal to mu 0 I times the number of coils in the toroid divided by 2 pi r, which is the basically the integral of dl. So that's the circumference of the imaginary Amperian loop. So we now say that it can be, it's inversely proportional to the distance, r, okay, of the Amperian loop. And of course, it's zero if it's, for per se, you draw an Amperian loop over here, right? The enclosed charge is zero, right? Because all the charges are basically over here and over here. And we're going to assume that, okay, the number of wires, right, that come into the page is equal to the number of wires that go out of the page. And therefore, if you draw an Amperian loop outside the toroid, okay, what's going to happen is the integral of dl will be zero because the enclosed charge, right, will be zero. All the number of wires, okay, whose current go into the page is equal to the number of wires that go, or the current that go out to the page. So they cancel out, and then you get that the magnetic field is zero outside or inside of the cross-section area of the toroid. So what I mean by inside is over here. When we say outside, inside of the toroid is essentially between in between the coil, okay, and that's where when you have a magnetic field. And it, all right, so we already defined little n to be the number of coils per unit length over here, right? So it's basically number of coils per distance, for the distance of this wire, of this coil. So if it's L, we know that if we have a circular coil solenoid, which is essentially a toroid, the distance will be 2 pi r, right? It will be the circumference. So we can say that lowercase n is equal to the number of coils, capital N, divided by 2 pi r. So we already have that over here. We have n over 2 pi r, and we can just call that n. And it's essentially the that we derived. So you can see is the same for a toroid and the same for a solenoid. Okay, so now we're going to take a look at what's going to happen. Okay, using Biot-Savart law, we're going to derive the magnitude of the magnetic field due to a dipole, okay, of a current dipole. And what I mean by a current dipole is basically we have a rod over here. Okay, we have a rod and it's connecting two wires. Okay, so one of the wires has current flowing out of the page. So this one over here comes out of the page, and then the other one goes into the page. Okay, so if that's the case, we have a current dipole. If you think about the force due to one wire on the other, you will see that they are in opposite directions, right? They are anti-parallel. Therefore, the force will be repulsive, but because they're attached to, with this rod, they will not, right? They will not be repelled. Okay, so then, what we can have here is that it can be a little bit of a tedious derivation, but I will show you, I will explain it to you with as much detail as I can. So suppose that you want to find, okay, the magnetic field at this point over here, point P. Okay, so in order to do that, you have to use the basic a basic understanding of the thumb rule, right? So per se, just for simplicity, we're going to start with one wire. So start with the left wire, and now use the thumb rule for that wire, and the current, comes out of the page, right? Because it's a dot. So it comes out of the page, and magnetic field will go like this. Will go in a counterclockwise direction. So if it goes in a counterclockwise direction, then that means that at point P, it has to be in a tangential, okay, direction to that circle. And what do I mean by that? So let me draw, I think I can do, yeah, I can do a circle. So suppose I have a circle, and this magnetic field that is produced by the wire that comes out of the page. And so we make it like that. So the magnetic field will be tangential at point P, right? Because using the thumb rule, the magnetic field is going in a radial direction, right? It's going to be circular. Therefore, since it goes counterclockwise, the magnetic field will be going like that. So like just like the green arrow. Okay, so it will be tangent to that circle, which is the magnetic field. And therefore, we can say over here that we can split this magnetic field, which is going to be an infinitesimal contribution, right? We're going to call this an infinitesimal contribution to the magnetic field at this point, because we also have to consider, okay, the magnetic field going from this point over here, right? So we also have to consider what's going to happen when you take a look at the other wire, right? The other wire goes into the page. For instance, what's going to happen is, so let me draw another one of those circles. What will happen, I wonder if I can do different color. Let's see. Okay, so what's going to happen is the same thing, right? So basically, it will be in opposite direction, right? So let me, it's too large. So this yellow circle will basically be the magnitude, okay, the direction of the magnetic field at point B due to the wire that comes out of the page. And that's going to be in the opposite direction of the other one. So what I mean by that, it will be like this. So at this point, it will be tangent to that. So we're going to have magnetic field coming like that. And this is essentially dB, right? So this is going to be dB as well. And so if you take a look, if we split this into two components, right? We split it into the X and the Y components. So we can say that this is going to be, just as the slides calls it, I'm going to call it dB perpendicular. And why perpendicular? Well, it's perpendicular to the Z-axis. So this vertical line that you see over here is going to be the Z-axis. That's what we call Z-axis. You can call it whatever you want. It could be the X-axis, it doesn't really matter. It's just for argument purposes. And so you split this into two components, dB perpendicular to Z and dB parallel to Z. This is called dB parallel to Z. Parallel. Okay. Now, if you think about it, the magnitude of this dipole wire, right? This current loop of dipole wire will be equal to 0 in the x direction, right? For dB perpendicular, which will cancel out, you don't have to calculate it in the x direction, right? For instance, what I mean by that, this and this cancels out for all contributions, right? And so what you're left with is dB parallel to Z, to the Z-axis. Okay, so essentially what's happening here is that you're going to have okay, to use Biot-Savart law. So we're going to use a few facts based on this triangle that we see over here. We know that this is 90 degrees. Okay, we're going to call the angle that makes ds. Okay, so the radial distance from here to here, r, and r, capital R, which is the distance from here to the center of the dipole. We're going to call that alpha. That's the angle alpha. Okay, which means that cosinus of alpha is capital R adjacent over hypotenuse, right? This over here. Oops. Uh-oh. Okay, there you go. So this cosinus of alpha is going to be capital R divided by little r. Using Pythagorean theorem, we can also find what r, right? R squared plus z squared, okay? Excuse me, r squared is equal to, okay, is equal to r squared plus z squared. Using Pythagorean theorem, we can find what r is, so r squared plus z squared, okay? And so using Biot-Savart law, we can derive an expression that we can integrate easily in terms of infinitesimal contributions of the angle d phi, right? So if we look at the top part, the top section of this dipole, so over here, we can see that the angle alpha, okay, will be the same over here. And that's because this angle over here is 90 minus alpha, okay? So using the Bernoulli angle theorem, we know that this angle over here must be 90 minus alpha. So this is let's call it alpha prime, okay, just because I don't have. So 90 minus alpha is alpha prime, okay, is equal to that. And so what happens when you have 90 degrees? So this over here, the distance between the angle between the two dBs on top. Okay, so I mean this angle over here is 90 degrees, which means that alpha prime plus alpha has to be equal to 90. And so alpha is going to be over here, okay, by the transverse angle theorem, okay, by the vertical angle theorem. And so from that, we can easily derive an expression using Biot-Savart law. Okay, so then we know that from Biot-Savart law, the infinitesimal contribution of the magnetic field dB is equal to mu0 I ds cross r hat. Okay. Now you have to think where r hat is going to be. We know already where ds is going to be, right? ds is essentially the direction of the wire. So ds is going to be coming out of the wire for the left side, right? Because the current is coming out. So ds is along the direction of the current. And then r hat is along the direction towards point P. So if this is distance r, then over here we have the unit vector r hat. Okay, so this is r hat. For instance, we know that if the vector ds comes out of the page, right, and r hat is always perpendicular to it, even though it's in a radial direction, that means that the cross product, right, must be equal to 1 times the magnitude of ds and r hat. R hat is a unit vector, so the magnitude of a unit vector is 1. Okay, so what we have is this over here. We have I ds sine of pi over 2, which is 90, and we just get I ds, okay, in the z component, dB. So then we can find the magnitude of the magnetic field in the z component, so dBz is equal to dV parallel, right? So dV parallel is basically the y direction, because that's the only thing that doesn't cancel out, right? And that's equal to dV times cosinus of alpha. Why cosinus of alpha? That's because using the fact that, alpha over here is the same, okay, as over here. And if we break this into components, and we know that dV is going up, then if we want to find what's going to be this component over here, knowing that this is 90 degrees, we know that this is going to be adjacent, okay? dB, the whole magnetic field. So this over here is going to be adjacent to the angle alpha, and dV, okay, dVz, okay. So this not this one. I meant dV parallel, okay. dV parallel is going to be adjacent, and then dV is going to be the hypotenuse, right? So what you do is you say that cosinus of alpha is nothing but dV parallel, right, which goes up, right, it goes in the upward direction, positive direction, is divided by dB, right, because it's the hypotenuse. Therefore, you can say, okay, you can say that dB parallel, okay, in terms of dB is basically multiplied by cosine of alpha. So you have dB parallel is equal to dB times cosine of alpha, okay, and then you plug in that into the equation. So we know that, okay, let's go back to B of R over here in the first formula. So stay with me. R squared, we know that's going to be square root of R squared plus Z squared, okay. So we put it in there. We know R squared is that. R squared over here, we found that's R squared plus Z squared. So we put it in the denominator, and we know that I ds cross R hat is I ds cosinus of alpha, right? Okay, so we're good. We can divide both sides by cosinus of alpha, okay? And then what happens here is that cosinus of alpha, okay, is nothing but the square root, okay, of R squared plus Z squared, okay? So that's the trick right there. And then what happens here is we're using an infinitesimal part of the angle. We can call this d phi, the infinitesimal angle that we're integrating. So let's say that this over here is d phi. And use the fact that the arc length is equal to the radius times the angle, then we have the equation as following. So ds is equal to r d phi, right? And therefore, we can substitute that in there. And so we're going to have that bz. We can integrate both sides. So bz is equal to the integral of dbz. So mu 0 over 4 pi times ir divided by r squared plus z squared to the 3 halves, right? Because that cosine in the bottom, okay, cosine of alpha is nothing but, right, adjacent over the hypotenuse. And adjacent over the hypotenuse, okay, so it's going to be r over this r divided by r. And that's where that comes from, because r is r squared plus z squared. So that's why we have r squared plus z squared to the 3 halves on the bottom, okay? And it's just a constant if you think about it, because we're not changing z, right? We're not changing r is just a constant. The distance r, okay, from one of the wires to the center of that dipole is constant. So what's changing is ds, okay? That's what integrating. The angle is changing. So we know that ds is basically an arc, right? So by the arc length formula, we know that it's the radius multiplied by the angle. So r d phi, and then we plug that in here into our equation. So then we bring that r outside of the integral, and we get ir squared, right? Because we have r over here. And think about that. Ir squared, that's pretty close to the, all you have to add in there to have an area is going to be pi. And I'll tell you why. So then you integrate d phi from 0 to 2 pi, right? Because you want to integrate the entire circle. Okay, and so what you're going to get is you're going to get that v of z is equal to mu 0 I times pi r squared divided by 2 pi, okay, multiplied by r squared plus z squared to the 3 halves. And this over here is the magnitude of the magnetic field due to a dipole, okay, a wire dipole. And so we know that the moment, right, the dipole moment is equal to the number of loops that you have multiplied by the current and the area, okay, the cross-sectional area. We already have the cross-sectional area, which is pi r squared, right? So it's essentially this is what I'm talking about, pi r squared. And we can substitute that to the dipole moment equation, which is I pi r squared is equal to mu. So then we know that if z is equal to 0, we're going to have mu 0, okay, which is going to be permeability times I divided by 2r. Okay, that's due to a long straight wire. And so we substitute mu into our equation. So basically, this is mu over here. This is mu. You're going to have something like this. You're going to have mu 0, mu, which is the dipole moment, divided by 2 pi times z cubed. But this is assuming, okay, that z is much greater than r. So basically, this over here, this distance z up to the point P is very large compared to R, capital R. If that's the case, we can say that R is pretty much 0. So we cancel out that and we get that z squared to the 3/2 is c cubed. And that's why this over here, okay? Which will simplify to be a function of z. So the magnetic field will be as a function of z, which is equal to mu0 times the magnetic moment, okay, the dipole moment, divided by 2 pi times z cubed. So it falls as 1 over z cubed. Okay, so it falls faster, much faster than, say, a long straight wire or a circular loop. Okay, and we can compare that with the result of a charge dipole. So when you have two charges, right, you can find the electric field due to these charges at an infinitely long distance, right? And we can found out, you probably went over this with Dr. Chin. It's going to be 1 over 2 pi epsilon 0 times P divided by z cubed, where P is the electric dipole moment. Okay. So the takeaway from this is that the common loops are the elementary sources of magnetic field. And the dipole 1 creates a field proportional to the source strength mu1. Dipole 2 feels a torque proportional to mu2 in an external magnetic field. So that means that mu2 cross B1 will be equal to the magnitude of mu2 times the magnitude of mu1, B1 times sinus of the angle between them. Okay. So let's take a look at what we have learned today. A quick summary. So we learned that in the previous lecture, we talked about the proportionality of force, the magnetic force, which is QV cross B. The force due to a current carrying wire is IL cross B. We talked about the magnetic moments, the dipole moment, the torque, which is mu cross B, and the potential energy, negative mu d dot B. Okay. I'm not sure if I derived the potential energy for you, but if you want me to derive the potential energy, just feel free to drop it on the chat and I'll do it for you. It's not very complex. It can be actually very intuitive. And so over here we went over V sub R, right? We know how this is actually coming from a very fundamental law in electricity, like Coulomb's law. Okay, so this is why Coulomb's law is more fundamental than Gauss's law. And we know that IDS is equivalent to QV. So therefore we use V sub R law for a moving charge or for a current kind of wire. Ampere's law is one of Maxwell's equations. Closed integral of beta ds, okay, is equal to mu0 I enclosed. And we also found the general, or per se, well, the general case of the magnetic field is V sub R law, right? But then the specific cases are when we solved, okay, the magnetic field using V sub R law due to a loop. This case will be mu0 I divided by 4 pi r times phi, right? And phi is that angle. So you can choose the angle to be anything, right? So if you want the angle to be 2 pi, so that means it's a full loop. If you want the angle to be half a loop, it's going to be pi, and so on. Okay, so we also talked about the magnetic field due to a solenoid and a toroid. We found that it's basically the same thing if we talk about the magnetic field to be in terms of the number of loops that it has per unit length, which is pretty much the same. Okay, but then if you want to be more explicit, then you say that the magnetic field on a solenoid, it's not included here, all right. So B inside of a solenoid is basically 0 times the current enclosed multiplied by the number of loops per unit length, where the length L is basically the length of that solenoid. Okay. For the toroid, it's already written here, and that's mu0 I times the number of loops per unit length. But the unit of length here is 2 pi r, right? Because you have a toroid, which is basically a solenoid, collection of solenoids in a circular manner. It's a toroid. Also, it's important to remember that the magnetic field outside of a toroid or outside of a solenoid is 0. Okay, it's negligible. And finally, with the magnetic field due to a current carrying wire dipole, B of Z, okay, as a function of the Z-axis. You can choose it to be anything. It could be X-axis, it could be Y-axis. And it's mu zero times the magnetic moment, mu, which we derived it, and we said that mu is basically the area multiplied by the current, right? And we only have one loop, so that's why n is equal to 1. So that's why mu becomes I pi r squared over here in this derivation. It comes out of the integral, and so that's why the magnetic field due to a current wire dipole is mu zero, the permeability of free space, times the moment, divided by 2 pi z cubed. And so, yeah, that's it for this lecture. Now we're going to take a look at the next lecture. This is just supplementary material. You can take a look at it on your own time. It's not necessary, but it's pretty good, you know, to empower, to increase your understanding of this section, this chapter. Okay, so now I'm going to move to the next lecture, next chapter on Faraday's law of induction, which is actually one of Maxwell's equations. So I'm going to stop sharing this one and I'm going to go to the next slides. Question?
Hello?
Yes. Yeah, I hear you. You have a
You're
question?
going to go ahead.
Sorry, what's that?
You're going to go ahead for chapter 29, right?
On Faraday's law, yeah, we finished sources of magnetic fields. We will start
Yeah.
with Faraday. Yeah, Faraday's law.
Oh, Faraday.
Which will probably go over maybe half of the slides, so that's good, so that they can catch up with the other section.
Yeah.
Yeah. So let me see if I can. I need to insert the other slides here. So, So if you have any questions, just let me know. In the meantime, I'm trying to pull out the slides for Faraday's law. You know, if you have any doubts of how we derived any of the equations, just let me know, and I'll glad to clarify it. Okay. Takes a while to print all the slides onto a OneNote, but that's fine. Let's have it here. I was having issues with the WebEx pens and the pencil, which doesn't work very well. It just crashes randomly. Just gonna use this, which is much better. Okay. So I hope you can see this. So, all right. So let's see. We talked about, okay. Initially, you went over what flux is, right? The first time you came across flux was when you saw Gauss's law of when you take the closed surface integral of a electrically charged particle, you can get the flux, the electric flux that comes out or comes into that surface, right? The imaginary Gaussian surface. Now we're going to talk about magnetic flux. We also said that according to Gauss's law, there are no magnetic monopoles. But why is that? Well, because if you take the closed loop, the closed surface integral of a magnet, right? So you draw, I think I showed you before, but I'll just do it again so you can understand what I'm talking about. So let's say you have a magnet, right? You have a magnet north and south. And of course, magnetic field lines flow from north to south. So then you're going to go like that, right? And suppose we have four lines, right? So let's say we have four magnetic fields and they are symmetric, right? So what happens is that if you take the closed surface integral, right, you draw an imaginary Gaussian surface around the magnet. This is a three-dimensional surface, right? When I talk about surface, it's a spherical surface. For instance, it's not a dimensional thing; it's a three-dimensional thing. It's going to be with surface area 4 pi r squared. So then when you take the surface integral of this magnetic field, you're going to find out if it's zero, right? If the magnetic field lines come outside of the North Pole, so for instance, the magnetic field lines come outside from the North Pole, right? They will go outside of that Gaussian surface. But then when they come back to the South Pole, right, it will just come back into the Gaussian surface. And so if you have these lines which are equal in magnitude, okay, over here we have the same magnitude, and over here we have the same magnitude. dA will be like this. Okay, dA will be like that, right? Will be perpendicular to the area. So when you take the closed surface integral, okay, of D, the magnetic field dotted with dA, find that is equal to zero. But why? Well, that's flux. As flux comes out, if it comes back in the same way, right, same magnitude, you're going to have net flux equal to zero. Okay, there's no net flux, and that happens for all magnets. So if you chop the magnet in half, you're going to get two different magnets with north and south pole, each of them. So you're going to have no magnetic monopoles. Okay, and that's why Gauss's law says that B dot dA is zero. But now we're going to talk about magnetic flux not for closed surfaces. We're going to talk about open surfaces. So we're going to talk about integral, okay, open surface of B dot dA. And now the flux will not be zero. Okay, that depends. Okay, let's say that we have a magnetic field flowing like this, right? So this is B, and the area, let's say it's some area, okay, like this, which has a vector dA like that. So this is dA. The angle between dA and B is zero. So cosine of zero is 1. So then we have that the flux is B times the area, the magnitude of the magnetic field times the area. So therefore it's not zero. But then of course, if you were to the surface, right? If we were to close, it will be zero. So that's the idea. We're also going to talk about something called electromagnetic induction, which essentially is the main topic in this chapter. Faraday's law of electromagnetic induction, which is extremely important in electromagnetism, in physics generally, and really for the world. Without Faraday's law, the economy will not be the same, right? Faraday's law runs the economy. Without it, nothing that you can use electronically would work. Right? Without our understanding of Faraday's law, nothing can work properly. And then we'll see why.
Before Faraday, electricity is battery. Power source is battery. They're limited power source, so it's usually the things working in the scientist lab, and in those days the gentleman scientist, you know. But using Faraday's law, you can see you can have many turns of a coil. You can move the magnet very fast, so you can generate very large, electromotive force, which is the battery power. So that's you can this is the basic the foundation of the generator. You can have hundreds and thousands and 10,000s of volts. A battery, each battery is chemistry, so it's 1.5 volts, right? So that's why Faraday's law is the foundation of the industrial commercial application of electricity. So that's why. So it's called the induction because the electromotive force, like the voltage from the coil, is generated because the magnetic field coupling, right? So it's called induction. There's no wire connected, because the magnetic field gets into the coil, then the magnetic field changes. The coil has a voltage like a battery, but this voltage could be very high. Okay, very good. When you go ahead.
Thank you, Shane, for the introduction. So yeah, essentially, before Faraday, there was this guy from Denmark, right? His name was Ørsted, and so he was a physicist, right, back then in the 19th century, and he found out, right, that electricity and magnetism, okay, for the first time, related. And how did he do that? Well, he took a compass and he brought it near a wire, current carrying wire, right? And that's when he found out that the compass was going to the north part of the compass will point in the same direction as the magnetic field lines due to a current carrying wire, right? Using the thumb rule, you can figure out in which direction it will flow. And so that's when people first started to think about the relationship between electricity and magnetism. And so after Ørsted, Faraday came, and then he did some experiments, mind-blowing experiments actually, that will show that these two phenomena are related. Okay, so we're going to talk about Lenz's law as well. Lenz is a Russian physicist, right? He basically his contribution to this law is extremely important because it's as a consequence of conservation of energy. But we'll see what I mean by that. We're going to talk about basic examples of transformers, generators, AC and DC voltage sources that can be produced with Faraday's law, right? Electromagnetic induction, and of course, something called an induced electric field, okay, that can be done using magnetism. Okay, so let's see. Lagging a little bit. Okay. So we already did the summary. Now, like I said, this flux due to a magnetic field now will be non-zero per se if the surface is open, right? So we have an open surface, the magnetic field has some magnitude, the magnetic flux. Magnetic flux is important here. And that's why we're starting with the basics, because this chapter has to do mostly with how magnetic flux will change. So the unit of magnetic flux is in Webers, which is essentially Teslas times meters squared. And you can figure that out by looking at the integral of beta dA. dA is basically an area, and B is magnetic field, so Teslas times meters squared. And so we talked about how the dot product works, so I think you're pretty familiar with that. But if you have some concerns, just let me know. Of course, the dot product is B times A times cosinus of theta, the angle between them. And so we can calculate the flux, the magnetic flux on its open surface easily using Gauss's law for open surfaces. Okay, so now here is the mind-blowing experiment that Michael Faraday did. So he just took a magnet, right? He took a magnet and he also took a coil of wire, right? And then he connected this wire to an ammeter. Remember that an ammeter measures current in amps, right? So here's the ammeter, right? And there's the coil of wire. So he puts the magnet into the coil and he brings it at a certain speed, right? So what happens is that he sees that there's a reading in the ammeter and there is current, right? But then, how can this be possible? I'm just putting a magnet into the uh, to the coil of wire. How can it be possible that current will flow, right? How is it that magnetism can create current? And so what happens is that really, if you think about it, the cross-sectional area of this loop is basically pi r squared, right? The radius of that loop squared times pi. And so if you multiply that by the magnitude of the magnetic field that comes from the north pole of that magnet, you can find the magnetic flux. And so if he moves that magnet, he brings it inside of that coil, what will happen is there will be a change in magnetic flux because the magnetic field lines are different if you move it, right? If you move it in or out, because the spacing between the magnetic field lines changes, right, in that cross-sectional area. So we have a change in magnetic flux, and that change in magnetic flux essentially is what creates current, right? Because if he brings the magnet in, right, and then he stops momentarily, there will be no current flow, which means that the magnitude of the magnetic field in the cross-sectional area of that loop is the same, right? But then if he changes, if he moves it again, he will see another reading, okay, in the ammeter. And this is Faraday's law of induction. A changing magnetic flux creates an induced current, okay, on a coil of wire or any wire, really, when you bring it close to it, when the magnetic flux changes. This is called also an EMF, so an electromotive force, which is not really a force, so don't get confused by the name. It's just a historical reason for why it's called EMF. It's just voltage, pretty much. But this voltage is induced, right? Because how are you going to have current if you don't have voltage, right? You have to have a battery. If you don't have a battery, how are you going to have current flowing? So what happens is that this magnetic flux, this changing magnetic flux, creates is pretty much like a invisible battery, right? It's an invisible battery that it creates. It generates a voltage, right? An EMF. This is what's called induced EMF. Okay, so this is Faraday's law, the basic principles. And of course, now let's talk about Lenz. So what Lenz said is that, if you are generating current, right, where is that current going to go, right? That current can just stay there forever. So this current itself, we know that from Biot-Savart law. We know that current generates a magnetic field around it. And this magnetic field, if you take a section of area, you can find the flux through that area, right? Using Gauss's law for open surfaces. And so what happens is that the changing in magnetic flux generates a current, right? But this current itself will generate a magnetic field around it, right? In such a way that it's, right, radially, okay? It's going to be in the radial distances, in different radial distances, and it falls as an inverse square distance, right? So it's an inverse square law. And so what happens is that this magnetic field that's created, that's generated by the current, it has to oppose the change in magnetic flux that is generated by Faraday moving the magnet in and out of the coil. And this is basically saying that, okay, energy is conserved, right? You cannot just create energy out of nowhere and keep it going and create motion or create electricity out of nowhere, right? This has to be opposed by that change in magnetic flux, by the magnetic field that's generated by that current. And so this is Lenz's law. Okay, that's why it's very important. Okay, so here is the quantification of Faraday's law. We have that EMF, which is represented by this Greek letter, epsilon. EMF induced is equal to minus n d phi b dt. Okay, and then d phi b dt is basically a change in magnetic flux with respect to time. So this can also be written as minus n times the derivative with respect to time times the integral, okay, of the integral of b dot dA, okay, b dot dA. And this is Faraday's law of electromagnetic induction. So a change in magnetic flux, which is integral of b dot dA, generates an induced EMF, which is voltage. And remember that from Ohm's law, EMF equals to the current I times the resistance R, IR, right? V equals IR. And so I'll show you a little trick that I learned recently. So if you take a look at this, okay, this is just miscellaneous, you don't have to know it. But if you take a look at this differential, okay, this differential outside of the integral can be brought inside of the integral, and that's differentiation under the integral side. But then you have to make it a partial differentiation. So it's partial integral of partial with respect to time, okay, of the magnetic flux b dot dA, infinitesimal magnetic flux b dot dA, and this is EMF, okay. And usually, this dA is omitted in some representations. So usually they just write EMF equals to minus m integral of partial, okay, of the magnetic field with respect to time. Okay, so don't worry about that. That's just, if you're curious, it's called Leibniz's differentiation under the integral side. But don't worry about that too much. That's just for curiosity. And so Lenz's law, of course, tells us that a change in magnetic flux has to be opposed by some other flux. So it has to be opposed by an equal and opposite magnetic flux, which is generated, okay, by that induced current. And this is called, of course, an induced magnetic flux, induced magnetic field. Okay, so Lenz says that an external torque, okay, must do work to keep whatever you're doing to turn, right? So if you have to have some source of energy in order to generate EMF, right, using Faraday's law. So if you have a change in magnetic flux, per se, you go to the central electric nearby, you're going to see that if it's close to a river, the motion of this river, right, the kinetic energy that comes out of the motion of water particles will transfer into magnetic energy. And so this magnetic energy must be conserved, right? So use Lenz's, the change in magnetic flux has to be opposed by an induced magnetic flux. Okay, so now let's take an example. Let's take a look at an example. Okay, using F equals QV cross B. Imagine you have a rod, okay, conducting rod, meaning it could be a copper rod or it could be any sort of conducting metallic material. And so this is moving at a speed v, constant speed v, in the positive x direction, just as shown. And you're going to have a polarization of charged particles. And that's due to the Lorentz torts. Okay, so what will happen is positive charges will go to one end of the wire, and negative charges will come to the other end. And if you have a polarization of charges in a rod, you're going to end up with an electric field, okay? An electric field that flows from positive to negative. So it'll go like this. This is the direction of the electric field, E. And so if you have charges in that electric field, then you can find the electric force on that charge due to the uniform magnetic electric field induced, okay? So the force is going to be Q times E. And so this situation, okay, when you have a uniform magnetic field, so the rod is flowing, okay, it's moving through a uniform magnetic field, B, that goes into the page, right? It's going to be represented by the crosses. Can be expressed, okay, this phenomenon can be expressed as a electrostatic equilibrium. So when you have electrostatic equilibrium, the magnetic field and the electric field forces must be equal. So then you say that QV cross V, the magnitude will be QVV, right, at a maximum, because as you can see, the angle between V and the magnetic field is 90 degrees, right? The magnetic field goes into the page, and the velocity is in the positive x direction. So then is sinus of theta is 1 maximum, right? And so they have QE is equal to QBD. So then you can find the relationship between the electric field and the magnetic field on a rod, on a moving rod. Okay, so then you have that E is equal to BB because the Q's cancel out, the charges cancel out. And so you have something called an induced electric field. And this induced electric field creates an induced voltage. Okay, and how do we find that? Well, we know that E is equal to V times the magnetic field. So then EMF is equal to the electric field times the distance, right? So the distance of the rod is L, E times L is the EMF, the voltage induced. So EMF is equal to minus BLV. And this is the equation that is going to be on the exam. They're going to give you that equation. EMF equals minus BLV. And this is used to find, of course, the voltage. When you have a velocity, the length of that rod, and you have the magnitude of the magnetic field going down into the page or out of the page, you know, in whatever direction they tell you. And so here's the schema. Magnetic force, okay, which is equal and opposite inside of the rod for any charge. So now, if the circuit, right, because this is essentially the imaginary battery I was talking to you about. It's kind of like an invisible battery. And so if you put, okay, some wire, right? So if you connect the top pole with the negative pole, you're going to complete the circuit. And this is essentially a circuit, right? If you put a resistor R, then you're going to have, of course, Ohm's law. You can find the resistance, and you know, using V equals IR. Okay, so now here is another example on how to, okay, another way to derive the previous equation, right? So we take the derivative of the magnetic flux with respect to time. Suppose that, you know, the magnetic flux is going to be BA, right? So the angle between BA and B is going to be the same, right? Zero. It's going to be zero. So BA cosine theta is going to be BA. And so we have BA dA dt plus dB dt times A used in the chain rule. But we know that if we have a uniform magnetic field, the magnetic field is constant. When you take the derivative of a constant, you get zero. So this term cancels out. So you're left with B dA dt. A is an area, right? So if you define the area, this infinitesimal area, okay, to be equal to the length times the infinitesimal distance dx, then you can plug that into here, and you end up with dx dt. But of course, dx dt, okay, the change in displacement with respect to time is nothing but the velocity, right? The first derivative with respect to time of displacement is velocity. So you end up with the same result, b times the length times the velocity, okay, EMF. Now, what happens when there is no motion, right? When there is no moving rod? How is that possible that you're going to have an induced voltage on a coil, right? So here's an example of a simple transformer. So over here you have a coil with N turns, right? You have a coil with N turns, okay? And then there is a ferromagnetic material inside of that coil. And that is so as to amplify, okay, the magnitude of the magnetic field. So it's stronger. And so what happens is that this behaves as a solenoid, right? It behaves as a solenoid, so that means that the magnetic field is only, it only has a magnitude, okay, inside of the solenoid. Magnetic field only exists inside, so outside is zero. So if you take the derivative of the magnetic field with respect to time, you find that it's equal to mu zero times n times di dt, okay, because the current is probably not constant, right? If you want to generate some induced voltage in that coil that's outside of the solenoid. So this blue coil is outside of the solenoid. It's not connected by anything, right? It's just close to that solenoid. And so this over here represents an alternating current voltage source, okay? And we have a resistor. The direction of the current is like that. Okay, so then what's happening really is that the Lorentz force is doing nothing, right? The F equals QV cross B is not doing any effect to create, okay, some induced EMF. So what happens is that there this change, right, in magnetic flux, because when you have an alternating current, right, you have a changing current, and if you have a changing current, you have a changing magnetic field because the magnetic field is generated by that current, right? And so what happens is that it's not constant, right? So if it's not constant, you have to create some sort of electric field. The electric field will be the end resort to generate an induced EMF. Okay, so there has to be an electric field that uh, flows through that coil and that will generate an EMF. That's why there's an induced EMF on the outer coil. Now, here we have an example of a rectangular loop. Okay, so it's moving in the positive V, positive X direction, and we have a, we have some polarization of charges. So on the top side of this rectangular loop, we have positive charges, and of course on the lower part will be the negative ones, which means that the electric field, right, should flow from top to bottom. So it's kind of like a parallel break capacitor, right? The problem is that it's connected, right? So if it's a connected loop, then there has to be a flow of charges. But now the question is, does current flow, right? Does it actually flow? Because it's moving in a uniform magnetic field at a constant speed. So what's really happening? So you have to think about what's happening to the flux. Is the flux changing with respect to time? What is flux proportional to? Right? What is flux proportional to? Flux, magnetic flux B, is proportional to field and the area, right? Dotted with the area. So if the area is changing, okay, then we know that the magnetic flux has to change. But then if the magnetic field is changing as well, then we also have, okay, a change in magnetic flux. So one or the other, or both at the same time, okay? But then if you
No, let me say something here, Juan. Because the Faraday law is E electromotive force, like the coil is like the battery. The coils, electromotive force, voltage, equal to minus N d phi mdt, right? Now, what is the flux? Flux is made of three things. Flux is B dot A, right? Magnetic field dot area. It's BA cosine theta. So now you want to change magnetic flux. You can change things. You can change the magnetic when set it. You can change the area when set it. You can also change the angle. Actually, in the generator, changing the angle, the magnetic field doesn't change. The coil area doesn't change. They change the angle. That will say the coil rotates. The coil rotates, then the magnetic field and the area, the angle changes. So that's how the generator works. So I think when said the two things, B change or A change, you can also change the angle. Maybe when said it, I didn't hear it.
Yeah,
the connection.
Right,
Yeah.
Dr. Chin is absolutely right. So B or A can change, right? But also because this is dot product of B and A, right? The dot product is equal to BA cosine theta. So if theta changes, the flux changes as well.
Yeah. So in the generator, is the angle change. In some other cases, you can change the B or change the A, but in the
Dr. Chin, are you there? I think we lost connection with Dr. Chin. Okay. And all right. Okay. So yeah, basically what he's saying is that if you have the dot product of DNA, then if you have EA cosine theta, cosinus of theta, right? Cosinus of theta. Then if theta changes, then the cosinus of theta changes, and therefore the flux changes, right? So either of these three parameters can change, generating a induced current, an induced EMF. So now in this case, clearly there is no change, right? There's no change in angle, right? This loop is not spinning in any way. It's not changing in area, right? You're not crushing this. The only way to change the area of this loop will be to crush it, right? To crush it or to expand it. And the magnetic field is uniform. So if the magnetic field is uniform, that means that it's not changing. B is not changing. So d phi dt is zero. Okay, so flux is zero. Therefore, there's no flow of current. Now, but what about this case, right? We have the same situation, but what's happening is that this loop it's coming out of the uniform magnetic field. Right? The magnetic field is constant, it's true, but now what's the area covered by the magnetic field? The area covered by the magnetic field is changing, okay, as a function of velocity, right? Because as velocity increases, okay, the area decreases. So it's inversely proportional. So therefore, d phi dt is less than zero. Okay, this is going to be negative, right? Because the flux is decreasing, right? Flux is proportional to the area. If the area is decreasing, flux is decreasing. So E equal to minus d phi dt. Okay. Now this is basically another an expanded example of Faraday's law. When you put a magnet into a loop of wire, this wire will induce this field, the magnetic field that comes from the north pole of the magnet will generate a current, right, in the loop. So you're going to have an ammeter reading. So now suppose that you have two circuits, right? One circuit with an ammeter and a loop, and that's all. And then the other one has a resistor, a switch, and a battery. So the battery has to, of course, supply voltage, right, to the loop. So when you close the switch, you're going to have an instantaneous change in current, right? Current is going to go up immediately, and it's going to generate, of course, a change in magnetic flux, right? Because if current changes, right, you're going to have a change in magnetic field instantaneously. So at that instant, when you close the switch, the other loop, okay, the loop that has no battery, is going to feel an induced EMF, okay? But of course, the induced EMF, okay, has to be opposed by that change in magnetic flux. So what do I mean by that? Okay, so think about it. Where is the direction of the current in the first circuit? In the circuit with resistor and battery, the current is flowing clockwise, right? If you think about it, if you were to move the circuit in such a way that it's clockwise, right? I1 is going to flow clockwise. So if you use your thumb rule, you're going to see, okay, that the magnetic field is coming out, okay, it's coming into the page. So essentially, it's already demonstrated here. So the magnetic field is going like that, right? So it's coming out like that. And so what happens when the magnetic field comes out like that in a cross-sectional area, right? With area pi r squared, where the radius is r. So the area is pi r squared, which means that, of course, integral of the open surface integral of b dot dA, right, is going to be nothing but b dotted with dA, right? But then because they're perpendicular, okay, well, they're really what's going on is that dA is perpendicular, right, to the surface, right? So dA is perpendicular to the surface, to the cross-sectional area. So dA is in the same direction as b. So we have b multiplied by a times cosinus of 90, I'm sorry, of 0, because it's in the same direction. That goes to 1. And so the area is pi r squared, so you have b times pi r squared. Okay. So now, what's happening is that this b, okay, this b is changing, right? It instantaneously changes. When you close the switch, the current flows in, okay, and then that is changing only in a very small span of time. So then what we can say is that dv1 dt is greater than 0, right? It's growing. v1 is growing as you close the switch, but it's very, very, very mild. It's very short time, okay? So now, my question for you is in which direction will the current flow for I2? Where will I2 flow? Clockwise or counterclockwise, and why? So do you have any suggestions? Where will it flow? Use the thumb rule to figure it out, right? And use Lenz's law. Anybody? I'll give you a couple of minutes to think about that. It's very important because it could be on the exam. You might have to use the thumb rule and Lenz's law together. Find the direction of the current in the other circuit. So you can unmute yourself or just type a message. Let me see. I didn't get the chat. Oh. So who has a suggestion? Okay. Let me know. Where will be the direction of the current for I2? Okay, if I1 is flowing in the clockwise direction, right? If you look at it, okay, from the left, so if you think about the magnetic field going into the page, right? I'm talking about this over here. Where will the current for I2? Is it clockwise or counterclockwise? Like this or like this? Somebody said the same direction. Okay, why do you think it's the same direction? So you say it's going to be clockwise, right? Why do you think so? Because the field's the same. Okay. Which field are you talking about? Field B1 or field B2? Because remember, I1 generates field B1, right? And I2 generates field B2. So which field is the same, B1 or B2? B1. So you say B1 is the same for I2. Okay. Yeah, that's right. That's right, because I2, right? If you do the thumb rule, B1 will be the same, right, for I2. But then remember that if you have a change in magnetic flux, so think about it in instantaneous uh, time, right? So you have a very small span of time when this happens, because when you close the switch, electricity travels at the speed of light, right? And it's an instantaneous change. That's why I call it instantaneous, because it's a very, very short amount of time that it takes for this change in magnetic flux to occur, right? Because B is going to be increasing, right? Since the current increases in 9-1. So I1 generates a field like that. So that means that B1 is also, okay, coming in the same direction through I2, right? So this is B1, okay? B1. But then what happens is you have to make sure, okay, that according to Lenz's law, right, it has to oppose, right? This, whichever direction it is that you choose, clockwise, you have to make sure, okay, that the direction of the magnetic field that that current produces has to oppose B1. So basically, I want to make sure that B2 goes in the opposite direction, like that. How do we do that? How do we make sure that B2 is opposite to B1? Because we have to generate, so if we generate a change in magnetic flux, it has to oppose, right? The current that we induce has to oppose B1. So B2 has to be opposite to B1. So which direction in the current will make B2 go in the opposite direction? Clockwise, there you go. Counterclockwise. So that's the key, Lenz's law. And that is why, okay, that is why we have, I don't know if I talked about that, but that is why we have this negative sign. The negative sign represents Lenz's law, because the negative sign is a consequence of conservation of energy. If you have, if you generate, okay, if you have a change in magnetic flux in one direction, you have to oppose that magnetic flux in the opposite direction to conserve energy, right? Energy cannot be created nor destroyed, so you can't just make energy. You can just make magnetic energy in I2 just out of nowhere, right? I2 has to oppose that, generating an opposite magnetic flux. So then, when you open the switch, right after you closed it, so if you wait for a long time, right? If you wait for a long time, after 10 thou, right? Let's say after 10 thou, 10 time units, the current will be a constant, right? Because you have a resistor and the battery supplies voltage. So the voltage across will be the same, the current will be the same, will be constant. It's not changing, right? Because it's direct current. It's a battery. So the magnetic flux will be zero, right? The change in magnetic flux is zero because dB, phi dt is zero. after a long time if you keep it closed, right? But then when you open it again, instantaneously, you have a change again in magnetic flux, and dB dt is less than 0. And so the current in I2 has to be in the opposite direction. So instead of being counterclockwise, it has to be clockwise now. So this is Lenz's law and Faraday's law. Okay, so here I tell you that the negative sign is for Lenz's law that basically represents the opposition of the change in magnetic flux. Okay, and so we have the induced EMF is equal to minus d phi b dt. Okay, so then now let's think about what happens when you have a spinning, right? You have a spinning loop of wire, right? So if you have a spinning loop of wire, okay, you're going to have a change in theta, right? So the cosinus of theta is not constant. If the cosinus of theta is not constant, that means that phi is not constant, it's changing. If you have a changing magnetic flux, you generate an induced EMF. Okay, so then we have several ways, right, to generate magnetic change in magnetic flux. So you change B, right? So you basically increase the voltage knob, right? So you could increase the voltage to increase the current, which will change B. You can change the area, or you can change the angle. Like I said, if it's spinning, right, you change the angle. So if this coil that I'm talking about, right, is spinning, to have a generator effect, right? And this generator effect is described by this function over here, this piecewise function, which is basically the magnetic field as a function of time. So as time goes by, okay, you're going to have a changing magnetic field, okay? And of course over here, dB dt is 0, so EMF is 0, okay? So it's a little abstract over here because they don't really have, it's just time B, A times B times C times B, and so on, right? This is when you have a spinning loop, okay? You can also graph it as a function of theta. And if you graph it as a function of theta, you're going to have alternating current because then, but I'll show you that later. For now, let's try an exercise over here. Okay, so I don't want to show you the answer, so go ahead and try this. A magnetic field through a loop increases by 1 teslas in 1 second. The loop in the loop area, okay, is 10 to the minus 3 meters squared, and it's constant and along the field. So basically, the area is not changing, but the magnetic field increases, so it changes in 1 second, 0.1 teslas, so from 0 to 0.1 tesla. So what is EMF? What's the induced EMF? Remember that EMF is minus phi b dt. Or if you don't have to deal with differential calculus, right? If you're just looking for the change, you have that EMF is minus delta B, delta phi B, right? Divided by delta T. So this is just a generalization without differential calculus. Somebody said minus 0.1. And what are the units? What are the units for EMF? Volts. There you go. So you probably did. Okay. So let's see. Let's see. Okay. So here's the thing. The area, right, is going to be pi times the radius squared, and you already have that. It's 10 to the minus 3. So then you multiply your changing flux, okay, which is going to be B times A, right? Phi B is B times A. So then B is 0.1 Tesla, and A is to be 10 to the minus 3. So you have 0.1 times 10 to the minus 3 divided by 1 second. That's nothing but 10 to the minus 4 volts. Okay, and let's say that they ask you to find the current. So if the current is described by Ohm's law, right, which is V equals IR, right? So you have I is equal to V over R. So you have the voltage, which is 10 to the minus 4 volts, Okay, and remember, don't forget the negative. Don't forget the negative from Lenz's law. Right, it's important. So then you have that EMF is minus, right, 10 to the minus 4 volts. So then if you want to find the current, all you do is you substitute V into here, and you get the current, right? Give resistance ohms. Okay, now let's take a look at, okay, we already did this, right? We found the derivation using the chain rule. We know that EMF is minus BLV, right, for a moving rod. But now we're going to consider the same problem, okay, but we're going to have two rails. These yellow things are rails, they're conducting rails. So they conduct electricity, and they are connected, across by a resistor R. Okay, so basically you're making a circuit, but it's a pretty weird circuit because the circuit is changing, right? Its area, its cross-sectional area is increasing because this rod is moving with a speed of v. Okay, so now if you do, you know that current flows from positive to negative, right? So if you do the right-hand rule, um, current goes up, magnetic field goes into the page, which means that the force has to go to the left. So there is a force, okay, opposing the motion of the rod, okay? Which means that if you want to keep this rod at a constant speed, you have to apply power. You have to apply work in order to keep it at a constant speed. So therefore, you have to have an opposite and equal force, okay, opposite to. And that, okay, what we do is we use, basically F equals IL cross B. Okay, so then to find the power extension, right, so that we can keep it at a constant speed, we can use I equal I squared times R, which is power, right? But we don't really have the current, right? We don't know what's the current. Um, so we want to find it in terms of the magnetic field, the length of the rod, which is L, and the velocity, okay, times the resistance. These are the parameters that we want to find it in. And so we know that power is equal to the force times the velocity, right? And how do we find that? Well, we know that, I don't know if you have seen it before, but it's a pretty cool derivation. So we know that basically power, right? Power is work, right? It's work done over time, right? So it's basically work over time. So change in work over change in time. We can call it dW dt. Okay. And so the work is basically the force times distance, right? So you apply work, and you have to apply a force over some distance. So we can describe work. So we can say that this is nothing but d times f, okay, times dx. Suppose the distance is dx. Okay, so let me actually, it has to be f dot x. There you go. Parentheses. dt. Okay. So what happens here is that basically, using the chain rule, that d df times x, right? Multiply, plus f times dx, and all of that divided by dt. Now, if we're applying work, right, we want to make sure that this force is constant, right? Because it has to be equal and opposite to f n, the force that I'm talking about. To be equal and opposite, it has to be constant force, right? It's not changing. So if it's constant, this term over here goes away. We have dx over dt. So dx dt is basically the first time derivative of displacement, which gives us force times velocity. That's where it comes from. So then fb will be replaced by the force, okay, acting on by this current wire, which is IL cross B, and you have B squared L squared V squared divided by R. Okay. So from this, you can find the power that you require on this circuit in order to keep the rod moving at a constant speed. I think this is a good point to stop, and hopefully we'll be able to finish by next time. So, thank you for coming. If you have any questions, just let me know. I'll try to post some videos up on YouTube regarding some practice problems that are similar to the exam that's coming up. So just pay attention to that. All right, so I'll try to post this later, this recording. I'll stop it now.